Hey, we've seen this before without the h's for sines and cosines, and here it is for the hyperbolic functions. So let's go. Let's follow exactly what we did before, but now we've got the hyperbola with this pizza slice that has a curved edge.
That's right. So we've got a little curved pizza slice. We've got our x naught here, which defines the point hyperbolic cosine of x naught, hyperbolic sine of x naught. Let's add an extra little slice like this, and this is going to be hyperbolic cosine of some x. X is small, we can think of it. Hyperbolic sine of x.
Okay, that's our skinny pizza slice, and then like we did in the cosine, we're going to rotate. So this guy is going to appear above the big guy.
Exactly.
Let's draw the picture first.
I'm going to draw it over here so we have some space. What we want to do is have this guy here with the x naught and rotate the other guy to here. So this is hyperbolic cosine of x, hyperbolic sine of x. Now this is a funny looking rotation because look, this little short line went long.
Well, that's because it gets skinnier up here, and that's because the hyperbola opens up. Mm-hmm. So that's a really interesting property of the hyperbolas, that for the circle case, the wedges just rotated and you can overlay them one on top of the other. Here the wedge rotates, but it gets kind of extended. So it's not just adding the area rigidly, but as we go up along the hyperbola. So that little wedge here that we started with gets pulled out and has this funny shape.
So let's write down this rotation matrix. It's a different rotation matrix, but it looks a lot like the one that we saw with the trig functions. We put the hyperbolic cosines in the corners. Up here, I put a hyperbolic sine. And this time there's no minus sign. This is a special kind of hyperbolic rotation.
Yeah, except that what we must remember is, where did the minus sign go? We started out before with the circle like this, and now with the hyperbola we have this, the unit hyperbola. There's the minus sign, and in fact that minus sign creates a whole new geometry that's used in special relativity.
Exactly.
So these kinds of rotations occur in special relativity.
Exactly, they occur in special relativity. And they have this interesting property that, remember, the cosh is like the x and the sinh is like the y. So cosh squared minus y squared is equal to 1. This matrix has determinant 1, which means it preserves area.
Fantastic. So let's see the algebra now, how we get magic.
This area here was x over 2. This area was x naught over 2. These areas add up. So that means this point has to be hyperbolic cosine of x0 plus x, and then hyperbolic sine in the y component of x0 plus x. Okay?
Yeah, we're done now. We just put in our vector point and
So
rotate
this point
it.
is the starting point, so I'll write it here. Hyperbolic cosine of x, hyperbolic sine of x. And when I rotate it, where does it go to?
Goes up there, like
Goes
in the
up to this guy
diagram
here.
over there.
So this gives me hyperbolic cosine x0 plus x. I'm just writing down what I have here. Hyperbolic sine of x0 plus x.
And I'll save you some efforts here. If we multiply cross to get this. So here's sinage x naught plus x.
Yep.
And it's going to be sinage of x naught times cosh,
Right there.
and plus cosh times sinage. Cosh of x naught times sinage. And there's the magic formula,
There's the magic
because
formula.
we have a hyperbolic rotation. And that's how we can get the derivative at any point that we wish.
So let's do hyperbolic cosine. So that's this guy over here.
cosh x naught times cosh x plus sinage x naught sinage of x.
Now this looks almost exactly like the trig formula, except we have a plus sign now.
That's right.
And that tells me that when I do derivatives, instead of getting a negative hyperbolic sign, I'm going to get a positive hyperbolic sign. So we found out last time that derivative of hyperbolic sine was hyperbolic cosine. And now derivative of hyperbolic cosine naught is sinh x naught. There we go.
And we got that same way we did before, is this is cosh x here, so we take this and subtract it to get our best approximation. This is equal to 1, so there's no slope. And we can see that sinage of x then from the same analysis is...
That's right. This is approximately x, and this is our slope.
So there we go. We now have the derivative of cosh at x equals x naught is sinage of x naught. Great job. Hey, we're in hyperbolics here. Let's see where we can go now.
I'm going to tell you something amazing. If you take hyperbolic sine and hyperbolic cosine, add them together, when you take the derivative, it comes back as hyperbolic sine times hyperbolic cosine.
Oh.
So now we get a function whose derivative is itself. And that's a very interesting function.
And is it related to hyperbolas again?
It is, in a very strange way, but it is.
But it's not the same. I got a feeling that rotation is waiting for us to see how we do something to this hyperbola.
There you go. This has been fun, Matt.
Fantastic.